Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Once 1830 when Evariste Galois on the condition for solvability of equations by radicals, the history of mathematics is punctuated by moments of profound reorientation, where the very questions being asked are transformed. Few such moments are as dramatic, as youthfully incandescent, and as tragically delayed in their impact as the creation of Evariste Galois' 1830 memoir on the condition for solvability of equations by radicals. This document, penned by a young man whose life was a whirlwind of political fervour and academic frustration, represents a monumental shift in algebraic thought. It moved the focus of inquiry from the pragmatic hunt for formulas to the abstract, aesthetic contemplation of structure. The work provided a definitive and startlingly beautiful criterion for when a polynomial equation could be solved using the familiar operations of arithmetic and the extraction of roots, a problem that had vexed mathematicians for centuries. Its methods, however, were so revolutionary, so alien to the established paradigms of the era, that the work's true significance remained a latent potential, a message in a bottle cast out moments before its author's demise, till uncorked by a later, more receptive genre. The intellectual stage for Galois' entrance was set by a long and distinguished tradition of algebraic investigation since the 16th century, with the successes of Supini del Ferro, Niccolo Fontana Tartaglia, and Ludovico Ferrari in resolving the cubic and quartic equations. The search for a general formula for the quintic, an equation of the fifth degree, had become a kind of algebraic holy grail. For 2 centuries, the finest minds made their attempts, all ending in failure. A fundamental change in perspective arrived with the 1770 publication of Joseph Louis Lagrange's Reflections sur la résolution algébrique des équations. Lagrange, in a masterful analysis of the known solutions for low-degree polynomials, made a pivotal observation. He saw that the key lay in the behaviour of the roots of the equation when they were permuted. By studying functions of the roots, which he called resolvents, he discovered that the solvability of the equation was tied to the way these permutations formed a system. He intuited that the structure of these permutations held the secret, though the full articulation of this structure eluded him. Lagrange provided the essential vocabulary and the conceptual starting point. Following Lagrange, the Italian mathematician Paolo Ruffini, in 1799, made a courageous and extensive attempt to prove the general quintics in solvability. His argument, while containing the core insight, was recognized as having gaps and a certain lack of complete rigor. The definitive proof of impossibility fell to the brilliant Norwegian mathematician Niels Henrik Abel in 1824. Abel, using permutation-based arguments, had built upon Lagrange's foundation, demonstrated with unassailable logic that no universal formula involving only radicals could exist for solving all quintic equations. Abel's proof was a landmark achievement, a definitive closing of a centuries-old door. Yet, it was an answer with a profound limitation. It declared the general case impossible but offered no insight into which specific quintic equations, such as x to the 5th power minus 1 equals 0, were perfectly solvable. The world knew that of impossibility it was Galois who would provide the why and, more importantly, that Galois' 1830 memoir, his definitive statement on the subject, is a work of breathtaking originality. Its central achievement is the creation of a direct correspondence between two seemingly disparate mathematical realms: the field extensions generated by the roots of a polynomial and the structure of a finite group of permutations. To each polynomial equation, Galois associated what is now called its Galois group. This group is a precise mathematical object, consisting of all the permutations of the equation's roots, and leave any algebraic relation between them, with coefficients from a base field like the rational numbers, unaltered. The group, in essence, captures the complete set of symmetries inherent in the polynomial's root system. A permutation belongs to this group if, after applying it, any valid equation involving the roots remains valid. This concept of a group of symmetries was itself a revolutionary abstraction. The memoir's core revelation, the condition for solvability, flows directly from this construction. Galois demonstrated that a polynomial equation is solvable by radicals if and only if its associated Galois group possesses a specific structural property, which today we call solvability. He articulated this through what he termed a proper decomposition. A group is solvable if it can be broken down into a chain of subgroups, one contained within the next, starting with the full Galois group and ending with a trivial group containing only the identity element. The crucial condition is that each subgroup in this chain must be a normal subgroup of the one preceding it, and the resulting quotient groups, the groups formed by the cosets, must be abelian, or commutative. This nested sequence of groups, This composition series precisely mirrors the structure of a solution by radicals. Each step in the group decomposition corresponds to the adjunction of a new radical to the field of numbers. The process of solving the equation, building a tower of field extensions like the rational numbers, then the rational numbers adjoined with the square root of 2, then that field adjoined with the cube root of 5, has a direct algebraic analog in the decomposition of its symmetry group. The solvability of the equation is a direct reflection of the decomposability of its group. This powerful theoretical framework provided a complete and immediate explanation for the long-standing mystery of the quintic. The Galois group of a general fifth-degree polynomial is the symmetric group on 5 letters, denoted S sub 5, which consists of all 120 possible permutations of 5 objects. Galois' theory required one to inspect the structure of this group. The group S sub 5 contains a large normal subgroup, the alternating group S sub 5, which consists of the 60 even permutations. The critical discovery is that this alternating group S sub 5 is a simple group. In the language of group theory, simple means it possesses no normal subgroups other than itself and the trivial group. It cannot be broken down further in the manner required by Galois' criterion. The existence of this indecomposable, non-Abelian bedrock within the symmetries of the quintic is the ultimate structural reason for its general insolvability by radicals. The algebraic obstruction has a name. It is the simple group S sub 5. This was an answer of sublime depth, replacing a puzzle of computation with a principle of abstract structure. The immediate impact of this masterpiece was, with a touch of historical irony, almost non-existent. The manuscript was submitted to the Paris Academy of Sciences, where it met a fate of incomprehension. An earlier version had been lost after being entrusted to Augustin Louis Corchi. A subsequent submission vanished after the death of its intended referee, Joseph Fourier. The final 1831 version was reviewed by Simeon Denis Poisson, a distinguished mathematician, who ultimately returned the paper with a dismissive note. He found the arguments obscure and declared himself unable to verify the reasoning, advising the author to provide a more complete and clear exposition. The issue was one of language. Galois was speaking in a new tongue of abstract algebra that the establishment, accustomed to calculation and geometric intuition, was unprepared to learn. This rejection, coupled with his increasing Republican political entanglements, further isolated Galois. His life ended in a duel in May 1832. The night before, convinced of his impending death, he famously spent hours frantically writing down his mathematical ideas, concluding a letter to his friend Auguste Chevalier with the plea to ask Jacobi or Gauss publicly to give their opinion, not on the truth, but on the importance of these theorems. The resurrection of Galois' work is owed almost entirely to the diligence of Joseph Liouville. In 1843, a full 11 years after Galois' death, Liouville acquired the young man's papers. Recognizing they contained something of profound value, he dedicated months to meticulously deciphering the Hermetic arguments. In September of that year, Liouville announced to the Academy of Sciences that he had found in Galois' papers a complete and correct solution to the problem of solvability by radicals. He published Galois' memoir, along with some of his own explanatory notes, in his Journal de Mathématiques Pures et Appliquées in 1846. This act of scholarly piety single-handedly brought Galois' theory into the mathematical mainstream and secured his posthumous legacy. The initial reception was one of awe and a slow, dawning comprehension. The ideas were still difficult, but with Liouville's imprimatur, mathematicians began the serious work of understanding them. The evolution of Galois' ideas charts a course toward ever greater abstraction and application. The first major figure to systematize and expand upon Galois theory was Camille Jordan. His monumental 1870 work, Traité des substitutions et des équations algébriques, was the first book-length treatment of the subject. Jordan clarified many of Galois' proofs, provided a wealth of examples, and firmly established the concept of the group as a central object of independent study. He moved the idea of a group from a tool for understanding equations to a fundamental structure in its own right. Jordan's treatise trained a new generation of mathematicians in the language of groups, making Galois' impenetrable ideas a standard part of higher algebraic education. This elevation of the group concept had consequences reaching far beyond the theory of equations. Felix Klein, in his influential Nietzsche 72 Erlangen program, proposed a revolutionary new vision for geometry. He argued that different geometries, such as Euclidean, projective, and affine geometry, could be classified and understood by studying the properties that remain invariant under their specific groups of transformations. A geometry, in Klein's view, is defined by its symmetry group. This was a direct and powerful generalization of Galois' core insight. To understand an object, one must understand its group of symmetries. The spirit of Galois was now at the heart of geometry. Concurrently, Sophus Lie was developing a theory of continuous transformation groups. now known as Lie groups, to investigate the symmetries of differential equations. This extended Galois finite, discrete groups into the continuous realm, creating a tool of immense power for mathematical physics, where Lie groups are now the fundamental language for describing the symmetries of the universe. From particle physics to general relativity, critiques of Galois' work in the modern sense have viewed it as a theory that has been absorbed so completely into the fabric of mathematics that questioning its core is akin to questioning arithmetic. The primary historical critique was the initial one of incomprehension, which speaks more to the revolutionary nature of the work than to any flaw within it. Subsequent developments have been ones of clarification, generalization, and deeper understanding. The language has been refined. For instance, Galois' notion of a proper decomposition is now articulated with the precise modern definitions of normal subgroups and quotient groups. Emmy Noether, in the early 20th century, further recast abstract algebra in terms of rings, fields, and modules, placing Galois theory within an even more general and powerful structural framework. The theory stands today, a perfect edifice whose foundations were laid by a single, brilliant young man against a backdrop of personal and political turmoil. The intellectual lineage is clear. Galois stood directly on the shoulders of Lagrange, taking the latter's study of permutations and elevating it to a new conceptual plane. He completed the quest that Ruffini and Abel had advanced, providing the structural reason behind their impossibility. Proofs, in turn, the influence radiating from his 1831 memoir is immense and ramifies through much of modern mathematics. Louvel was its saviour, Jordan its great expositor, Klein and Lie were its most ambitious generalizers, exporting its central principle to geometry and analysis. The work of later algebraists like Richard Dedekind and Heinrich Weber, who developed the theory of ideals in number fields, and the aforementioned Emmy Noether, all built upon the structuralist viewpoint that Galois had pioneered. In conclusion, Evariste Galois on the condition for solvability of equations by radicals is far more than a solution to an old problem. It is a paradigm shift. It taught mathematics to ask a new kind of question: what is the underlying symmetry structure? The essay redefined the meaning of a solution, from a formulaic recipe to a deep understanding of structural properties. The work's poignant history, its repeated rejections, its author's tragic fate, and its posthumous vindication serves as a perennial reminder that the most profound ideas may require a period of incubation before the world is ready to receive them. Galois created a language to describe the very limits of algebraic expression, and in doing so, he gifted mathematics one of its most powerful and unifying concepts. The legacy of that youthful, frantic night of writing in 1832 is a testament to an intellect that saw, with perfect clarity, an abstract world of symmetry invisible to everyone else.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.